Hello, in this video, I am going to prove that the sum of any two even integers is even. Now you might be saying to yourself, that's easy enough to do, right? We could just choose two even numbers such as, 2 and 4, which makes 6. We could just say, that's easy. 2 and 4 makes 6. 6 is even. We're done here. No, not quite. Since this particular 2 plus 4 is equal to 6, that's a very specific case. And we don't want just a specific case. We want any case, given by the fact that we want that the sum of any two even integers, not just specifically 2 and 4. So the general approach to doing something like this is first establishing that we have two even integers. So we want to establish two even integers and then show that their sum is even. And to accomplish this, we need to use a variety of definitions and whatnot. But first, let's define two integers, shall we? So, if we let n and m be integers, or be elements of the set of integers. Alright? Now, we could easily just say even integers to begin with, but again, already stating them to be even is a very specific case, like 2 plus 4 is equal to 6. We don't want specifics. We want a general case. So we first start off with those two being integers. And we'll continue that with such that, and this is the part where we establish the even integer portion, such that n is equal to 2 times a different integer, let's call it k, and m is equal to 2 times a different integer, let's call it w, where both k and w are integers. So you might be looking at that thinking to yourself, well, that looks weird. Why do you need 4 different integers in order to show 2 of them to be even? And again, that's due to the fact that we want this to be a general case. We don't, no matter what integer we choose for k and w, we're trying to make both n and m be even, which will happen when you just multiply that number by 2. And to show it beyond a reasonable doubt that the sum is even, we need to establish that first. Just like how in a courtroom, the prosecutor needs to show beyond a reasonable doubt that the defendant's guilty. Here we want to show beyond a reasonable doubt that any two even integers, their sum makes another even integer. And so we want to show that no matter what integer we start with, being odd or even, that we could then show that the even integers specifically add to make another even integer. So we establish that first, specifically by the definition of even integers. Is how we could say this. Definition of even integers. So now we want to add the two of them, right? That's the whole idea of this. So now, if we add n and m together, using the fact that n is 2k and m is 2w, this is equal to 2n plus 2w, which we could just do by substitution, right? since we already have these definitions. But then, since we have this 2n plus 2w, we could, I broke my own definition on there. This is supposed to be 2n and 2w, 2k and 2w. So we have 2k and 2w. Now, from that, we could say, but 2k plus 2w is equal to, we could factor out these twos, a 2 from both of these since they both share a 2, 2 times k plus w. And this factorization is from the idea of the distribution property. So this would be by the distribution property. By the distributive property. But now, we can let's say j equal to k plus w. With again, j being an integer. And how do we know that j is an integer? Because since we're adding two integers, the sum of two integers is another integer, since the integers are indeed closed under addition. Since the integers are closed under addition. Alright, so now we could just substitute in that j. So 2 times k plus w would be equal to 2 times j by substitution again. And then we could say that n plus a more legible m, is equal to 2 times j by the transitive property. By the transitive property. And we know that because we have all these equalities throughout this proof, showing from n plus m all the way down to 2j. But by that definition of integer numbers again, by the definition of even integers, this then means that n plus m then is even, which shows that the sum of those two even integers is even. So, based upon that, we are now done with this proof.